Okay, so our next speaker will be presented by Diego. So Diego is the host of the second speaker. So Diego, it's
okay. Thank you very much, Felipe. So it's a great pleasure to me introduce Professor Cristian Morales Rodrigo. Professor Cristian has received his PhD in 2008 at University of Warsaw in Poland under supervision of Professor Mirosław Lachowicz, and in 2009 by the University of Seville under supervision of Professor Antonio Suarez. Professor Cristian is an associate professor at the University of Seville since 2021, and he has supervised two PhD students, and he's around 30 papers and almost 500 citations. And today he's going to talk about local and non-local problem in elliptic PDEs. So Cristian, welcome. So the word is yours. Cristian, the microphone. Hello, Cristian.
Now? Okay.
Yes. No, it's okay.
Now? Okay, yes. Okay, thanks, Diego, for this kind invitation to the seminar. So first of all, what I'm going to talk is about the no results about the local problems, and then I will say something about the non-local problems, mostly in elliptic PDEs, but I will we connect with parabolic PDEs. Okay, the first thing I will, as an introduction, so I will introduce some kind of motivation. We will be interested mostly. So the idea is that we have a domain, and around the domain we have, let's say, we are thinking in that the domain is an habitat of some kind of species that live in this domain. So in the domain, what we have is basically a species, and we consider the density at any point S at any time t. So one way of describe the density is by a parabolic equation. So you have ut, and then you have some kind of motion that in this case we are considering the diffuse operator, the Laplace, and then we have some kind of reaction that can be described as f of su. So the diffusive operator, what it gives us is a way in which the species is moving. So basically, you may think that the species can spread around the domain at the same probability at any point. So basically, if I think just in 4 points, then the probability to move left, right, up or down is exactly the same. So, and in this kind of motivation, because we are thinking mostly in the densities of a space, of a species, so what we are going to think is mostly about functions that are positive. So we have this problem with initial data that is a density, they have to be positive. Okay, this f of u is the difference, the reaction term is basically, I'm thinking in the difference between the bonds and the depth of the species. So we have motion given by the Laplace, and the f, that is the reaction that it gives us the chain of the population. So let's say that if we think very, very, very simple, one of the simplest cases that you have the linear. Okay, so basically you have a lambda. I mean, lambda is a parameter, and then functions. This is probably one of the most simple equations that is well known what it happens. So basically, if you have some kind of growth that is small, you may think lambda determines the way in which the species is growing. If lambda is small, less than this lambda 1, that is, this lambda 1 is basically the principal eigenvalue of the minus Laplacian. So what happens is that your solution basically goes to 0 as time evolves. And by contrast, when lambda surpasses this lambda 1, then what happens is that your solution is growing to infinity as time evolves. So basically, we have a change of the stability of the 0 solution, basically. And this lambda 1, as I say, is the principal eigenvalue of the elliptic operator minus Laplacian. But phi 1 I will be considering as the eigenfunction. So basically, is the only one that does not change sign. The rest of the eigenfunctions change sign. And you may say that this lambda 1 also is the spectral radius of the inverse of the minus Laplacian, so basically. So as I say, what we have in the linear case is a chain of the stability of the 0 solution between in lambda 1. So if lambda is smaller than lambda 1, then the solution goes to 0. While if lambda is greater, then the solution goes to plus infinity. There is a chain of the stability of the 0 solution. Then the second case that is well known also what happened is the sublinear case. So basically you have a parameter and then you have a power that is between 0 and 1. And then you think about what happened in the parabolic case. And in order to do that, first you have to imagine what happened with the stationary solution. So, and basically what happened is that you have that if lambda is less or equal than 0, then by the maximum principle, then your solution has to be less or equal than 0. We are looking mostly, as I say from the beginning, U as a density, so you don't have a solution greater or equal than 0, where lambda is less or equal than 0. Whereas if you may say, okay, what happens when lambda is greater than 0? So if lambda is greater than 0, you have a solution, and the way to construct that solution is by the method of super solution. So here are the sub and the super solution. You may say that for epsilon small enough and for m large enough, then you have that this has an order. And then you may prove using basically the super solution method that for any lambda greater than 0, you have a positive solution. Moreover, you have uniqueness of solution, or uniqueness of positive solution. So, and is a result of Brezisov of 86. So basically it's because the function that you have here, when you divide by u, is decreasing. So this implies uniqueness of positive solution. And you can even go further and construct basically how are the solutions. Because you take just the solution for lambda 1. So you take the U1, the solution for lambda equal to 1, and the rest of the solution is just a simple computation, can be computed directly. You can verify that this U lambda is a solution, a positive solution, and because it's the only one, so you have your solution, your positive solution, basically. So this is let's say local problems, and when we give with a little bit more difficult problem, okay, yes, what happened basically, again, the idea is the same as I said before, is that there is a chain of the stability of the zero solution in lambda equal to 0. So a new solution emerged that is called this U lambda, and what happens is that let's say the system is tending to this U lambda solution where lambda is greater than 1. And if we grow the difficulty, let's say a little bit more, you may see the third case, that is the logistic equation. First, in the case where B is separated from 0, so the real logistic equation. So in this case, is well known what happened with the solution. If you study the stationary solution of the logistic equation, you can prove that there is a unit solution for lambda greater than lambda 1, and you can construct the solution using, for example, this sub solution, the epsilon bar phi1, and the super solution large n. Actually, the large n is one way to construct the super solution, but let's say they are a little bit more difficult, but it gives you more information. Instead of using n, you can construct another super solution that gives you a little better knowing what is happening around lambda 1. Because basically you around lambda 1, you will have a bifurcation from 0, and you cannot capture this bifurcation with this super solution. But you can capture with a kind of perturbating the domain. In any case, this is what we have here is the simplest, one simple proof to show that there is a solution for lambda greater than lambda 1. And uniqueness, again, this function, when you divide by u, is strictly decreasing. So you can, again, use Bresee-Southwell proof. And what happened, again, the idea that I try to convince you all the time, basically, is that there is a chain of the stability of the zero solution. If lambda is less than lambda 1, is stable, while if lambda surpasses lambda 1, then it's unstable, and it goes to the unit solution of the stationary problem. Basically, this is what is happening here. And a little bit more complicated is the case in which you have what is called a refugee. So basically, this B is not strictly separated from 0, it's banished as some subset. So imagine this connected subset. It has to be, for this kind of technique, these two sets have to be regular, basically. And what happens is basically in this subset, the function is like B is 0, and the function is behaving like like a linear case. So that's why it's called a refugee, because it refers basically to a place in which the population cannot die because of this term. It's basically growing all the time in this subset. And again, the idea is, okay, what happened with the parabolic case? Let's think a little bit. And what happened is that is lambda, this change dramatically the behavior respect to the logistic growth when B is separated from 0, because you have a positive solution only for a large a range of lambda between lambda 1 a lambda 1, this omega b0, that basically is the Dirichlet operator just in the Laplace Dirichlet operation just in this subdomain omega b0. Again, you can prove uniqueness of positive solution. Is Bressy Thorwald. It's not strictly now decreasing, but you can, let's say, do a kind of adaptation and prove also that there is uniqueness of solution. You can, and this is a little bit more complicated, to prove that between lambda 1 and lambda 1 omega b0, you have a solution. The sub-solution, you can use either the super solution method. The sub-solution, it will be exactly the same as before, this epsilon on bar phi 1, but the super solution is a bit more complicated to construct. So, but you can prove that there is a super solution. So, and this will allow you to prove that there is a solution between lambda 1 and lambda 1 omega b0. And also what happens is that when lambda is going to this lambda 1 omega b0, then the solution is behaving as what is called here is a meta solution. So basically, I have a picture in the next slide. Basically, if I see in one-dimensional domain, what is happening is that it's growing to infinity at the boundary of the omega b0. So it's a kind of this kind of solution. Okay. And what is happening basically is that what is happening is that we have the behavior of the solution is going is behaving like this the solution of this problem. So it's basically a meta solution because it's 0 at the boundary of omega at an infinity in the boundary of omega b0. Then what's basically happening in the first case is that the solution is going to 0 if lambda is less than lambda 1. Then it's going to this solution that we know that exists between lambda 1 and lambda 1 omega b0. And then if lambda is greater than this lambda 1 omega b0, then it's going to infinity. So you have a blow up, basically. This is the local problem. So again, I insist one and another time that there is a chain of the stability of the solution 0 between in lambda 1. Okay. Then another case that is a little bit more complicated is the concave convex case. So what happens is in let's say the first result or the results I'm talking about is in this paper by Ambrosetti, Bressy, Zirame. And what happens is that this P is less than the P critical and Q is between 0 and 1. Also, in the paper, there are results even when P is equal to P critical. But here in my talk, I will not comment about that. So basically, what happened is that there is a lambda that if this lambda star is large enough, you don't have a positive solution. And basically, the proof is rather simple. You take just the bar phi 1 as a test function in the equation, and you realize that this function that I have here for lambda greater than 1 is less or equal than 0 for for every t positive. Then you can prove also that there is a minimal solution for every lambda between 0 and a lambda star. You can construct again this solution by the super solution method, but for such a lambda. And you can also construct a second solution that in the paper of Ambrosetti Precisamente they did by the mountain pass lemma. So basically what happens is I represent the solution in the y-axis, the norm of the solution in L infinity, and here in the s-axis the parameter lambda. What is happening is that is a solution that is growing as lambda evolves. Then as lambda star you have a solution, but then a second solution appears between this 0 and lambda star. This solution is unstable. It's proved by basically it's because you construct by the mountain pass lemma, and the solution that you construct is unstable. So basically what happens again is that you have a chain of stability of the solution of 0 at lambda equals 0. So in all the local problems, what I have shown basically is that there is a chain of stability at some particular lambda, either lambda equals 0 or lambda equal to the first eigenvalue. So basically, then this is the well-known results about the local problems. And let's talk a bit about the linear case. Okay, in the linear, in the non-local problem in the linear case. So basically, we put a function that depends on an integral of omega of some up. P can be greater than 1. Pardon, P greater than 0. Just don't need to be P greater than 1. And I try basically to know what happened in all the cases I've been dealing before, except probably the last one because I will not have time, basically. So the idea of what happened in the linear case when you have this kind of non-local problem. By the way, we are not assuming, this is important, that this A is positive for S greater than 0, but it can touch 0 at 0. And even this A can go to plus infinity at infinity, if I think as a function. So basically, we are not assuming that the A is bounded neither from below or from up, basically, because most of the results before in the literature, basically, we were dealing with A was bounded from upper and from below. And we don't have such assumption. It even can vanish at 0, okay? Not in other points, but at 0 can vanish. And then what happens is basically we didn't know this lambda 1t that is eigenvalue that depends on the Laplace with a weight here that is minus a st. And we didn't know by lambda sup and lambda super the infimum and supremum on this lambda 1t. And then what know is that this lambda sub bar is greater or equal than 0. Of course, it's less than this lambda star, and it is less or equal than infinity, basically. And the result is set basically for the linear case that if lambda is between those two values, that I said before, then we have a positive solution. And we can indeed construct the positive solution, because you take this lambda between this lambda sub and lambda super, and because of the continuity of this lambda 1 respect to t, because we have a continuity, you know that for such a lambda, there is some t0, that is lambda 1 t0. And then you take, you try to construct the solution. So basically you say, okay, I look for my u as a function multiplied by the eigenfunction function associated to this lambda 1 t0, and you force calculating k using that basically is the integral of up equal to t0, and then you construct the solution. You have uniqueness when this A is monotone, but in other case, you don't have uniqueness in general. We haven't proved it, but in general, it shouldn't be true. That in order to have uniqueness, you need a kind of monotonicity of the A function respect to variable t. And of course, if this A of A0 is 0, then this lambda sub bar is 0. And if if the limit goes to infinity uniformly in omega, then this lambda omega, this lambda super, it could be plus infinity. So basically, let's say that the linear case was well studied in the paper. Then, in the growing a little bit the difficulty, and okay, what I'm going to tell here is when it's not vanished at 0, but in the paper also it can vanish at 0, basically. But what I tell here is when it's separated from 0. But in the paper, we can deal also in the case where A vanishes exactly at 0. So, and the idea here, basically what I would like to say is that you can construct an operator, or let's say, the idea is to use bifurcation theory. So in order to use bifurcation theory, you need a compat operator. So a way of obtaining the compat operator, first of all, well, what we do is basically to have a compat operator in which your solution, either you have 0 solution or you have positive solution. So one way to do it, to force just positive solution for the operator, is changing the problem, and instead of using u plus, the positive part. Okay, and then you inverse, take the inverse of the Laplace operator, basically, and this is a compat operator. And then what you look basically is for a solution when u is equal to the inverse of lambda u plus this thing, basically. And then you can look like a kind of thesis point, or as the 0 of a perturbation of identity minus a compat operator. So basically, the idea is you have a positive solution if and only if this operator that I have here is equal 0. So, and a way to study this perturbation of this compat operator by identity is the degree theory. So, and here is a mistake. This is the boundary of the ball. So basically, the degree theory is a way in which you construct a, let's say, a function that it can be constructed that said that the identity of the ball at 0 is equal 1 if 0 is in the ball, basically. And an important property that is well used in the degree theory is the homotopy invariance. So basically, if you have an operator, it's more general than this. If you have an identity minus a kind of tk that is independent of t, in the sense that 0 is not at the boundary of u e minus tk of the ball. If this degree is invariant respect to t, is the homotopy. Basically, this is, let's say, what is called admissible. If you have this, then you have a homotopy invariance. It's a well-known, let's say, choice just to prove the degree. So, and basically, one important property is that the degree is different than 0, means that you have a solution in your ball, basically. And the index of the solution is basically the degree of I minus k in some small ball, basically. And what happened is that in this case, you can prove that you have index 1 if lambda is less or equal to 0, and in the 0 of the 0 solution, lambda is greater than 0. So this will mean basically that you have a bifurcation point from Q0. The advantage of this method is that you don't need regularity. Okay, you don't need that this is C1 because UQ is not C1 as 0, basically. Then what we proved here is that it will be fast. That you have this kind of limit. If it's plus infinity uniformly in omega, then you have solution for every lambda. And if not, you have a function that is tends to some function or even 0 uniformly in omega, then you don't have the positive solution for lambda sufficiently large. And if you have some monotonicity of A respect to S, you have existence and uniqueness of solution. You can prove, say basically that the solution that emanates from lambda star equals 0 is goes to infinity in soon. Oh, this is why I put 0. Okay, it can be 0 if C is 0, but basically what we can prove is tending to this C uniformly in omega that is going to plus infinity as some lambda star. And this lambda star, we can prove that E0 is C0, basically, what is written here. And then finally, the most complicated case, that is the logistic case. But here it's important that the function A does not depend of A, of F, of the space variable. Is a function that depends just on the non-local term. And it's important because as some part of the proof, we will be using a fixed point argument. We cannot use it if we have a function, basically. And again, as I say before, this A can touch, is separated from 0, but can go to 0 or plus infinity at infinity. So basically, here in a compact set, basically it's separated from 0, but and bounded. But when you don't have, when you go to infinity, it can go to plus infinity or even can go also to 0. You don't need to be this A bounded from neither upper or below. And this B, again is a function that is greater or equal than 0. This R is greater than 0, and Q can vanish also at some part. So what we can prove, and this, for example, this result can be done also when depend on S. Let's say we can basically use the bifurcation, and we can prove that there is an unbounded continuum emanating from this value, this lambda 1 A 0. And also we can prove that it's going to plus infinity at this A infinity lambda 1 omega b omega 0. So in all the cases, but mostly in the situation in which, let's say, the set in which B vanish and Q vanish does not contain the set in which Q vanish or the omega b 0. It can be either separated or it can touch, but it cannot contain. So in this case, we know that there is a bifurcation from 0 at 0 lambda 1 and from infinity at infinity lambda 1 omega 0. And in the most complicated case in which, let's say, the set in which Q vanish contains all the set in which B vanish, then all the results depend on this I. This I, remember, this was the meta solution. It was the meta solution that I was describing before. That is the solution that basically is going to infinity at the boundary of omega b 0, and is 0 at the boundary of omega. Then what happens is that you define this GS, that is S divided here, and you try to know this set, this GY. Let's say the values in which S reach the value Y. So, and the situation on what is happening is can be very complex. So imagine that you have this GY is let's say the empty set. So all this G of 0 is 0, because as I say, this A0 is separated from 0 in this case. Then what you have is that you have a solution for every lambda greater than lambda 1 A0, in this case. In the case that you have this GY with just one point, what will happen basically is that is going to plus infinity at this capital lambda 1 that is brighter here, basically. And if you have, for example, 3 points, then you have solution between A0 lambda till this capital lambda 1. Here we don't know what happened, and between S2, S3, this that you have associated lambda 2 capital, lambda 3 capital, you have a solution. And moreover, if you have some kind of monotonicity of A, you can know that those solution goes to plus infinity in norm, as lambda goes to this capital lambda 2, and well, lambda goes to this capital lambda 3. Probably it's true in general, but we cannot prove it. So basically, you have a solution, and if you think in general, you have solution in between the set in which G is below this I. So this is basically a little bit the idea of the general theory. And this is all that I wanted to say. Many thanks for your attention.
Thank you very much, Christian, for your very nice talk. So now we open the turn for question, comments. So if anyone has some question or comment, please raise your hand or just open your microphone. Okay, so Christian, I have one question because everything you did in bounded domain, right? Or you have...
Yes. I have to be in a bounded domain.
Yes.
This omega has to be a bounded domain. Yes.
Okay. And what happened in the situation where you have an unbounded domain? Is there any result in this? Is it possible to? Is it possible? But I mean, is it interesting to study this class of problems?
I haven't seen. I will have to remember. I know that let's say with bifurcation you can try if you are growing the domain basically to study the problem in balls that are becoming bigger, and then you can use maybe a kind of topological lemma. I don't remember any lemma of Weber, just to try to prove maybe that there is a solution. But as far as I know, I don't remember any results for okay, maybe yes, there are results for the sublinear case in the Bresisowa paper, but let's say in most of the cases I will have to think what happened in a domain that is abounded. But as I say, one of the techniques that I may think about is that just to start with a ball that is growing to infinity.
Yes, exactly.
In all these balls, you can use, for example, the bifurcation theory, but then you have to know what happened with the ball is going to infinity. So
yes, exactly.
as I say, the way I may think is that to use the Weber lemma, I don't know, it will be possible to do it. But as far as I know, I haven't seen results in this direction.
Yeah, you need to some kind of uniform estimating of the the parameters that in order to make things uniform, right?
Yes.
Okay. I have another question. Is that in the equation that you present, you have here the non-locality is in terms of an integral of the solution. Is there any result, or is it possible to have some result where you have the integral of the gradient of the solution? The norm of the.
It's like, well, you are thinking, for example, in the divergence form, so something like divergence of this A of A, or you want to change the function.
Yes, instead to consider the LEP norm here, you have a I don't know some norm of the gradient of U, because you see in fluids you have some model, some non-local model, which is called Izmagorinsky model, where the viscosity of the fluid is non-local, and the non-locality is a gradient. It's the gradient of
okay. But this is more complicated. So let me.
Is it Is it possible? I don't know if people call this
I'm not, I don't
Bischoff.
sure. Let me try. But just fighting with the, but I don't know why. Let me, yes, let me close this
Yes.
and open the, so you are thinking something like, I'm not
A
sure
of
of that.
X. Yes. No, you have A of X. Yes, just right.
Okay.
A of X and for instance, the L2 norm of the gradient of U.
Okay. The L2 norm of the, not the, okay.
Gradient,
Yes.
gradient of U. Yes.
But this,
Where?
but this is the Kirchhoff if I.
Yes, it is the Kirchhoff, no? The Laplacian of U times Laplacian of U.
Something like that.
Yes, and yes, yes. Is there?
Yeah, well, this is what the Fabricon were, but I don't remember if they have this.
The Kirchhoff, right?
The Kirchhoff equation, we have results also about the Kirchhoff equation. It's you can, let's say, the key point is that if you want to have results in the easiest way, basically, you need to use a kind of physics point argument. And the issue is that if this depends of S, it made the things more difficult. I don't know in this case, I hope, and I think it's possible, but I'm not sure, that you can use a general result like bifurcation theory. You need some kind of bounds, of course, you need something. I think a general result probably could be applied in the, like bifurcation theory, could be applied for this kind of equation. What for sure you want to give something very precise what is happening with this brand that is emanating from at some point, let's say, to have a good description in general, we cannot do it when it depends on F. It can depend of just the gradient of U. But this problem is a bit more difficult. It's I think it's more easy the other one. But you can still apply a kind of physics point argument for this problem because this is a number. So basically, what you need is that what you have here is a number. If it's a function, you cannot. But you can apply, as I say, the general bifurcation theory. We haven't done in this paper we haven't done because basically what we wanted is to describe well what is happening with the unbounded continuum that is emanated from this lambda this at some point. If you don't have, basically what is happening is that if you don't know, if you have some F function, it's very difficult, and I don't know even if it's possible to know what happened with this continuum that emanates from some point, basically. And that's why we eliminate in the logistic case the function that is depending of S. And in this case, I bet it should be. I think the bifurcation theory probably could be applied, but it's also more complicated because from where is emanating? What is an eigenvalue of this kind of problems? Because one eigenvalue, basically, probably here you need some kind of dependent. Let's say one property very important of the eigenvalue is that if you have this is eigenvalue, some constant by the eigenfunction will still some constant should be also an eigenfunction. And if you have some norm here, you are, let's say, introducing some C to some power. So it's a bit more complicated. And these kind of problems are studied, if I remember well, in something like ball. You have uniqueness and stuff like that, because it should be something like lambda u to power 3 or something like that, because of these two that you have here. So basically, it's more complicated, this problem that you are saying, even because also you have the issue about what is the linearization at some point of this kind of problems. It's more complex. So I know that we have some results for using bifurcation for the Kirchhoff equation, but let's say the Kirchhoff equation is more complicated.
Okay, Christian. I have just a last question
Okay.
from my side. Is you have the result that you present is just for an equation, right? What about when you have a system of equation with no local terms?
This is okay. Yes, this is the next step, basically. We are doing actually with Marcos. Marcos, I think is here, or I was before. And yes, we are doing stuff like that with Marcos, basically, when you have a system. So you put some function in front, some integral of u, but here you have more possibilities, basically. You have, because you can put that interact with UV and the other also with
I know.
EU, blah, blah, blah. And,
or even
and then, or even with the same, with
both.
Or you can have also even more complicated with cross diffusion and stuff like that. But the first step, basically, with Marcos Viana.
You see, the model that I mentioned, the Smagorinsky model. You have. Let's say it's the same A in all in each equation, because you have U is a vector field, the velocity of the fluid, and then you have the same, let's call the same A involving the sum of the integral of the three components of the velocity field. You see. Okay. Thank you, Christian. Is there any other question or comment? If not, let us thank Christian again for your very nice talk. So now I give the word to Felipe.
Okay, thank you, Diego. Thank you, Christian. Thank you, Gabriel, the two speakers. Very